Thank you, Joseph. Okay, so let's go as usual. Let's go over the solutions to the checkpoints of last time. There were two checkpoints. This is the first one. So so for those of you who answered correctly the question, can you just tell us what is the correct answer and why is that the correct answer? Okay, be brave. Yes, so that is correct. The correct answer is C, because it depends on whether the socket is a TCP socket or UDP socket. So if you recall from the lecture, UDP socket, it's just based on essentially the destination port number, but a TCP socket is identified by a 4-tuple, which is the destination and source IP address and destination and source port number. Okay, so it depends. That is the correct answer. Okay, now let's look at the next one, the next checkpoint. What is so I'm going to ask you the same thing. So if you answered correctly, would you care share with us what is the correct answer and then why is that the correct answer? Okay, since I didn't hear anything, I'm going to give you the answer. In Go backend, so remember, to answer this question correctly, you need to remember what is the definition of the receiver window. The receiver window is, by definition, the range of sequence numbers that will be accepted by the receiver. In the case of Go backend, the receiver will only accept the next sequence number, right? So if it receives any packet with a sequence number that is different, it will not accept it. So the receiver window in Go backend is of size 1 because it accepts only one sequence number. And the correct answer is B. The selective repeat, in selective repeat, the receiver window is of the same size as the sender window. So if the sender window is capitalized N, the receiver window size is also capitalized N. Any question on this one? Okay, if not, then let's okay, so I see. Yes, correct. So Mohammed made the comment that since it doesn't have buffer, it doesn't buffer the packets which are out of sequence. It has to not accept them, right? Basically discard them. So that's why the receiver window size is 1. Yes, actually, let me see. I did send an email to the TA, and let me see. Okay, hold on, bear with me. I think there was they will be great. So homework 1, homework 1 and homework 2 will be graded before test 1. But homework 3, because the due date is the day before test 1, so obviously it cannot be graded before test 1. However, the solution will be posted, so I would really strongly encourage you to study the solutions of the homeworks. Okay, and then just a quick announcement. So I have sent an email out to you yesterday. I have posted some questions on Piazza, and those questions, I have set them up so that you're going to work in teams. I have split the class into 4 groups. So all the students within one group should work collaboratively together to answer a question, right? So there are 4 questions, and each group is assigned 1 question to work on. So within your group, work collaboratively with the other students so that you come up with the best possible answer. And the question will be worth 10 points. Now, the points that you earn, they will be pure bonus. What that means is that they will be added to your homework total. You also have the option to work on the other questions, the ones that are assigned to the other teams. And for these other questions, if they are not assigned to you, they will be worth 5 points each. Okay, so in the best case, if within the team you answer correctly all the 4 questions, you are going to earn 25 points. Now I will need the answer. I will need the answer by the end of tomorrow. Okay, so tomorrow 11:59 p.m. Essentially because I'm going to go over the answers on Thursday. The reason is that these questions, they are relevant for test 1. Okay, question, how do you know who has worked on the optional ones? What do you mean who? This is a collective effort. So this is a kind of a team score. You will get. Does that answer your question? So if the group, for example, answer correctly 1 optional question, everybody in the group will get 5 points. Now there will be partial credit, right? So in order to earn the 10 points or the 5 points, your answer need to be 100% correct. Okay, now let's go back to resume the lectures. Is there a way to see who is in our group? I don't think there is, and I'm not so familiar. I'm not familiar enough with Piazza. I'm not sure I know the answer, but normally whoever is in the group can participate in Piazza, and I will be able to see who posted, who participated. Okay, let's go back to flow control and congestion control. So just to refresh our memory, let's go back a few slides. When the TCP connection begins, so first, what we see here is the plot of CWND, which is the congestion window. And the congestion window is the size of the window that will constrain the sending rate of the sender, right? So the idea in TCP is that if the sender thinks that there is a congestion, the sender will reduce CWND. And if the sender thinks that the concentration level is low enough, it will keep increasing CWND. Okay, you're not seeing the slide? Okay, I don't think the problem is on my side because other students are seeing it, so you may need to, I don't know, go back and, log off and log back in. Okay, so that is essentially the principle in TCP, right? And the CWND is used for congestion control. Okay, so when the TCP connection begins, the sender has no idea whether the network is congested or not. So it's going to start with a very low value, the lowest possible value of CWND, which is 1, right? 1 packet, 1 segment, which is what we have here. And then it will send the packet, send 1 packet, and then stop because the window is 1. Wait for the ACK. When it receives the ACK, it will increase the window by 1. It will increase CWND by 1. So after 1 round trip time, so here transmission round from here to here, we have 1 round trip time. So after 1 round trip time, the sender, so here I assume that everything is fine, it receives the ACKs, right? The sender receives an ACK, it increases the CWND by 1. So now CWND is 2. Because the window is 2, the sender now is allowed to send 2 packets. It sends 2 packets. And again, I assume that there will be an ACK for each of these 2 packets. So each of the ACKs will increment CWND. And now CWND is 4 after 1 round trip time. Okay. And then, so you can see with that trend, what happens is that every round trip time, CWND is double, right? So it starts at 1, and then it's 2, and then it's 4, and then 8. And this mode of operation of the TCP sender is called slow start. So that's what I showed in blue here. Okay, slow start. That is the mode when the sender increases exponentially CWND. Okay, now you cannot keep going. Well, eventually there will be a packet loss, right? And I assume that the packet loss happens here at this point in time. Okay, packet loss. So here I assume that the packet loss is detected by timeout, loss from timeout. When the loss is detected by a timeout, CWND will be reset back to 1, regardless of whether it's TCP Tahoe or TCP Reno. They both do the same thing when there's a loss by timeout. And they both set CWND back to 1. That's one thing. The second thing they do is that they're going to update another variable, SS threshold. Okay, SS threshold, so do not confuse SS threshold with CWND. They are 2 different variables. They're going to update SS threshold to half of CWND when the loss happens. So in this case, CWND is 8, right, when the loss happens. So now SS threshold is set to 4. Okay, 4. So this is, here I plotted SS threshold. And SS threshold is simply used by the TCP sender to know when it should switch from slow start to congestion avoidance, which is what is shown in red here. Okay, so it goes back to, CWND goes back to 1, goes back to slow start. So again, we do the exponential increase. But now the difference here is that we have a SS threshold value, which is 4. So when the CWND value reaches that threshold value, the CWND will still be increased, but more slowly. Here, this is a slower increase. This is a linear increase, not exponential increase. And this is what I show in red, right? And this mode of operation is called congestion avoidance. Okay, so it switches to congestion avoidance when CWND reaches the value SS threshold. And it keeps increasing, right, as long as there's no packet loss. And here, assume that packet loss happens at this point in time. So every time packet loss happens, SS threshold will be updated to half the value of CWND. In this case, CWND is 10. So SS threshold is updated to be 5. Okay. Now, I also assume that this loss is caused by timeout. So because it is caused by timeout, CWND is reset to 1. And it goes back to slow start, increase exponentially until the time where it reaches SS threshold. And at that point, it will switch to congestion avoidance. Okay, so I keep doing that. Okay, so this is one case where you have the losses caused by timeout. And then I think I told you last time, but I think it's good to repeat. The reason why after it has a loss, after it has experienced a loss, the reason why it will exit the slow start and switch to congestion avoidance at half the value of CWND is that if it stayed in slow start, then we can see that at the next, after one round trip time, at transmission round 8, CWND will be 8, right? We are at 4, so if we have one more round trip time, it will be double. It will be 8. Now the sender knows from the past that at CWND value 8, there was a loss. So this is a kind of guess that the sender is making based on the past experience that considering the, the current congestion level of the network, it is likely that it is, if it goes to CWND 8, it may have a packet loss again. Okay, it's not sure, but because that's what happened last time. So here when we're at 4, we don't want to stay in slow start because if we stay in slow start, we'll go straight to 8. And there's a good chance that we may have packet loss again. So this is getting kind of close to the danger zone, which is CWND 8, right? So it's going to proceed more cautiously, increase CWND, but linearly instead of exponentially. Okay, so that is the rationale why set SS threshold to half the value of CWND when the packet loss happens. Okay, now let's look at another case, which is we have a loss by timeout, but we also have a loss by 3 duplicate acts. And now here I need to assume that it is TCP Tahoe because the TCP Tahoe and TCP Reno, they don't behave the same way when there is a loss from 3 duplicate acts. Okay, I see there is a question for Andrew. What does SS threshold do again? So I don't know when you posted that question, but did I answer your question in the meantime or not? Okay, so SS threshold is simply a way to memorize. SS threshold is a variable or state variable that defines a threshold, right? As the name implies. Actually, it stands for slow start threshold. So when the sender increases CWND, and when the CWND value reaches the value SS threshold, it will switch to congestion avoidance here. So it switched from slow start to congestion avoidance. Okay, and then I have explained why the value of SS threshold is set to CWND divided by 2. Okay, that part you follow, right? Okay, so the so here you see SS threshold, right? So whenever there's a packet loss, it is updated. Here we have another packet loss, so SS threshold is updated. All right, so here we have a case. So it starts like on the previous slide, slow start. We have a packet loss by timeout. CWND goes back to 1. SS threshold is set to 4, exactly like on the previous slide. But here, the second loss is caused by 3 duplicate acts, not by timeout. So TCP Tahoe does not make a distinction between timeout and 3 duplicate acts. So whenever there is a loss, it doesn't matter what caused the loss. TCP Tahoe will set CWND to 1. Okay, back to 1, and then back to slow start, meaning exponential increase, until it reaches SS threshold, at which point it will switch to congestion avoidance. Okay, now if it's TCP Reno, it matters whether the loss is from timeout or 3 duplicate acts. So this part is the same as before, right? As the previous slide. But here, the loss, here because we have TCP Reno, and because we assume that the loss is caused by 3 duplicate acts, so TCP Reno will reduce the CWND when there's a loss from 3 duplicate acts, but not as drastically as setting it back to 1. Okay? Not always if it's TCP Reno. You can see here, right? This packet loss does not make the CWND go back to 1. What it does instead is that it will divide CWND in half and then add 3. So the new value of CWND will be, in this case, it was 10. So if I divide by 2, it will be 5. I add 3, it is 8. So it is a new value, 8. Okay, so now, because 8 is higher, is greater than the SS threshold. This is my SS threshold. So like before, right? SS threshold is updated to be CWND divided by 2. So SS threshold is updated to be 5. And because 8 is greater than SS threshold, so it will increase, it will stay in congestion avoidance. Right? So whenever the CWND is greater than SS threshold, it is in congestion avoidance, meaning that from this point on, it's going to increase the CWND linearly, not exponentially, until there's a packet loss. Okay, any question on what we have seen so far? And I think this is where we stopped last time, and I told you that I will explain to you why there's a +3. So the reason why TCP Reno does not, when there's a 3 duplicate acts, the reason why TCP Reno does not reduce CWND drastically down to 1 is because if there are 3 duplicate acts received by the sender, well, first, that is a sign of packet loss, okay, granted, but the loss is not as severe as the case of timeout, because when there is a timeout, really the sender receives nothing, no acts, nothing, right? Nothing came back, okay, which is, if you compare with the case where it still received 3 duplicate acts, okay, it's reasonable to say that if the sender received 3 duplicate acts, there is congestion, of course, because the packet is lost, but the congestion is not as bad as the case of timeout. Because in the case of timeout, everything is lost while nothing came back, no act. In this case, the sender received 3 duplicate acts, so the acts went through, the acts were not lost, and also these 3 duplicate acts, they were triggered by the reception of 3 packets. So there were 3 packets that went through that triggered the 3 duplicate acts. Yes, it was linear before the tree duplicate tax. Yes, correct. It was linear. Here, it's linear. Okay, so this is congestion avoidance. So as long as CWND is, if the CWND value is greater than SS threshold, it is in congestion avoidance. So here just kind of reduce the value of CWND, but it stays in congestion avoidance. Any other question here? Okay, so it's a kind of simple rules. There are just a few simple rules you need to know about the CWND, right? The first thing is timeout. Loss caused by timeout or pre-duplicate acts. If it is caused by timeout, it doesn't matter what is the TCP version. They both reduce CWND to 1 and go back to slow start. That is the first thing. Now, if the loss is caused by 3 duplicate acts, if it is TCP Tahoe will reduce CWND to 1. If it is TCP Reno will reduce it using this formula. Okay, so it does not go back to 1. Okay, the second thing is SS threshold. So SS threshold is a different variable than CWND. You can see clearly this is SS threshold. This is CWND. And SS threshold is updated at every packet loss. It doesn't matter what caused the loss, right? It doesn't matter if it is timeout or three duplicate acts. It doesn't matter if it is TCP Reno or TCP Tahoe. Whenever there's a packet loss, SS threshold is set to CWND divided by 2. And the third thing you need to know is SS threshold determines the mode of operation of the TCP sender, right? So if CWND is greater than SS threshold, it is in congestion avoidance. If it is lower than SS threshold, it is in slow start. Okay, so Emmanuel, I see you type a question, but it seems to be kind of incomplete. Is that, I'm not sure I understand your question here. Does it mean that the timeout and loopback determines? But then the question stopped there, so would you care to elaborate here? All right. Okay, so now let's try to understand why we add 3, right? So actually this is a slide, I'm going to show you a slide that I have added. So that is usually something I do on the whiteboard, but now because I teach online, and my whiteboard is not working very well. I don't have really a good whiteboard. So I created a slide. And I did that, I think yesterday or the day before yesterday. Okay, so this is a new version that I have posted on eLearning, which has this added slide. So let's assume we have a room. So you can think of it like an exhibit room in a museum. It has a limited capacity, right? So this is very crowded, but okay, it has a maximum capacity of n people. The room can hold n people. Now, if there are more people than the capacity of a room, then the extra people, they have to wait in line. Okay, so there's a queue of people waiting here to get into the room, but they are not admitted into the room. They have to wait. So first question for you, at what point in time will the person at the head of the queue here be admitted into this room? When? They're not going to wait forever, right? At some point. Yes. So essentially, when somebody here leaves the room, so that gives there's one slot available, so the one person can get admitted into the room. Okay. So when somebody leaves the room, then somebody from the queue can be admitted. So that can happen Okay, so one person leaves the room, another person enters the room, and then one more person leaves the room, another person enters the room, and we have this kind of situation, right? 3 people left the room, so we can admit 3 new people into the room. Okay, now let's look at that means for computer networks. My room is going to be the network, the computer network, and here my computer network has a capacity of n packets. Essentially, I say capacity of n packets because so these are the packets which are in transit in the network, right? They are on their way to the destination. They're inside the network, but actually the network has a capacity because if there are too many packets in the network, there will be congestion, right? We want to avoid the congestion. So you can mentally think that the network has a capacity of n packets. Okay, we don't want to exceed that capacity because that will cause congestion. Okay, now I have a TCP sender who sending packets into the network, and the TCP sender maintains a window, right? The window, and the which determines the rate at which it can send packets into the network. Okay, now remember this CWND is reduced to be CWND divided by 2 plus 3 when there's a packet loss, which is detected by 3 duplicate acts, right? So the sender, at the sender, the event is inception of 3 duplicate acts. Okay, if I have 1 duplicate act, what does that tell the sender? That does tell the sender that so the duplicate act came from the receiver, and the duplicate act is triggered by the reception of out of order packet, right? That's why you have a duplicate acts. So here we have a packet that has left the network. Now, if we have 3 duplicate acts, that tells the sender that 3 packets have left the network. They have left the network and received by the receiver, and that is why the receiver sends the duplicate acts. So we have exactly the same situation here, right? 3 packets have left the network. It's like 3 people have left the room. And therefore, we, at the sender, we can add 3 more packets, right? We can add 3 more packets. We can send 3 more packets into the network, exactly like here. And that we're not going to exceed the capacity of n. Okay, so add 3. Now, how does that translate in terms of the sender window? Essentially, add 3 plus 3 segments to the sender window. Okay, so that is essentially a kind of intuitive explanation why add 3. Any question here? So we'll say that is a bit the rationale behind adding 3. Okay, so I have a question. Does it have to be 3? So can you clarify what do you mean? Do you mean that does it have to be 3 duplicate acts to determine that there's a packet loss, or? Okay, why acts are not considered individually? What do you mean by considered individually? Okay, okay. Let's handle one question at a time. So the first question is, does it be 3? Yes, but there could be 3 duplicate. There could be more than 3 duplicate acts, but when there are 3 duplicate acts, it is enough. So this is the logic of TCP. So we have learned about that in the previous lecture. The logic at TCP is that 3 duplicate acts, it is considered that there has been a packet loss. Now, you may have more than 3 duplicate acts, but 3 is enough, right? So if there are 3 duplicate acts, the sender considered that there is a packet loss. Okay, so that's just a kind of, I mean, it's not a kind of scientific mathematical proof, right? That 3 duplicate acts is really a proof of packet loss, because you could have 3 duplicate acts caused by delayed or out of order delivery. There's no packet loss, but simply the packets came out of order. And if it just happened 3 times, you have 3 duplicate acts. But it's just a kind of empirical rule that they decided to use for TCP. And I think in practice, it works pretty well. Okay, so these are the two ways sender detects packet loss, right? Timeout or 3 duplicate acts. Okay, the next question, why acts are not considered individually? So that one I don't understand. Can you clarify your question? Essentially, at the sender, the rule here is that it must see 3 duplicate acts before it determines that a high chance that there's packet loss. Okay. All right, so let's look at the finite state machine with congestion control. So initially, we start in slow start mode. Okay, and this is the initialization steps. So CWND is initialized to 1 segment. SS threshold is set to 64 kilobyte. So 64 kilobyte is some value that is very large. And essentially at the beginning, in reality, the value of SS threshold doesn't matter. SS threshold has a meaning only after there has been a packet loss, right? Because that is when it is updated to be CWND divided by 2. But initially, so it's just some kind of placeholder we have. And then the sender has to maintain the counter of duplicate acts, because if there are 3 duplicate acts, it should take some action, right? Essentially detect that there's been packet loss. So this is initialization. Okay, in the slow start mode, whenever there is a duplicate act, it will increment the counter. Okay, if there's a new act, so a new act simply means an act which is not a duplicate act, right? A normal act, if you wish. It's going to add one MSS to CWND at one segment, right? MSS. Okay, now the duplicate act counter will count consecutive acts which are duplicate. So if there's a new act that is received, which is by definition a non-duplicate act, then the counter should be reset to 0. Okay, so receive act, increment CWND. So this is how we achieve the exponential growth of CWND, because if we increment by 1 at every act, then we double CWND after a round trip time. And then it may transmit new segments as allowed by the window. Another possible event is that it has been waiting for the act, but the act never came, so there's a timeout. So here we are in the case of what? Loss by timeout, right? Loss by timeout. So update SS threshold because we have packet loss. Reset CWND to 1 MSS. Reset the counter of duplicate act to 0. Now, because there's a packet loss, retransmit the segment. Okay, so in this state, it grows exponentially, the CWND, right? Now, eventually, the one thing that may happen is that, okay, it reaches the value of SS threshold, at which point it needs to transition to congestion avoidance, which is this state. And in congestion avoidance, it's going to, if there's an act which is a non-duplicate act, it's going to grow the CWND, but more slowly. Here, this is going to be a linear growth. So instead of at every act, instead of adding one MSS, it's going to add only a fraction of an MSS. And this is a fraction, MSS divided by CWND. Okay, so a fraction at every act. So after it has received CWND acts, then CWND will be incremented by one MSS. Okay, because this is less than one. The value of this quantity is less than one. Okay, so this is a slower incrementation or a slower increase of CWND, which translates into that linear increase on the curve, the CWND curve, right? Okay, and then like before, if we have a new act, then reset the counter, duplicate acts. Transmit new segments as allowed. So if the window allows, then transmit new segment. Duplicate act, count the duplicate act. So if there's a duplicate act, increment the duplicate act counter. If there is a timeout in this state, this is the event, a timeout. Reset the CWND to 1 MSS. Go back to slow start. Update SS threshold. So here, because this is a packet loss, so update SS threshold. Reset the counter duplicate act, and retransmit the packet that has been determined to be lost, right? Lost by timeout. Okay, now we have another type of event, which is 3 duplicate acts. So duplicate act counter is now equal to 3. So here, this FSM is for TCP Reno. Okay, so just to be clear, this is for TCP Reno. So when there's a 3 duplicate acts, okay, because this is a packet loss event, update SS threshold to be CWND divided by 2. And then set CWND to be SS threshold, which is CWND divided by 2 plus 3. Okay, this is the reduction of CWND, but less drastic than setting back to 1 MSS. Retransmit missing segment. And then it will go to this state. So I haven't told you about this state we call fast recovery. I'm not going to go into all the details, but give you an idea of what happens in this state. Okay, now the idea in this state is that because what may happen is the sender may receive, for example, 6 duplicate acts, right? 6 duplicate acts. So the question is, if there are 6 duplicate acts consecutively, should it be handled like 2 events, each event being 3 duplicate acts? And the answer is no, because if you have 3 duplicate acts, it will go into this state. And in this state, as long as there's duplicate acts, it's not going to reduce the CWND. Okay, there's no reduction of CWND. In other words, if you have 6 duplicate acts back to back, it is handled like a single loss event. Okay, single loss event. So this is what we see here, right? So if there's one more duplicate act in this state, then it's going to it's not going to do this reduction. Okay, now in this state, what may happen is that it may receive a non-duplicate act, in which case it goes back to congestion avoidance. Okay, so set the CWND to be SS threshold, reset the duplicate act counter. Now, if there's a timeout, go back to slow start and do the same thing as here. So SS threshold is CWND divided by 2, reset CWND to 1 MSS, reset the counter duplicate ACK. Now in this state, if we have 3 duplicate ACK, then it will do the same action as here. Okay, so SS threshold is set to CWND divided by 2, and then CWND is actually reset, updated to be CWND divided by 2 plus 3, and go to this state. So the key points about this FSM is that no matter what state you are in, no matter what state you are in, if you have a timeout, go to slow start. Okay, here, if there's a timeout, go to slow start. Here, if there's a timeout, go to slow start. And go to slow start, reset CWND to 1 MSS, reset the duplicate ACK counter, and update SS threshold. So here you can verify that no matter, throughout this FSM, whenever there is a packet loss, whether it's caused by timeout or 3 duplicate ACKs, SS threshold is updated to be CWND divided by 2. Okay, the second thing is no matter what state you are in, if you have 3 duplicate ACKs, you will go to this state. And you will update your SS threshold, right? And set CWND to be CWND divided by 2 plus 3. Okay, so I think these are the key points. And then this is also another key point is that when you are in SS threshold, if CWND reaches the threshold, then go to congestion avoidance. Okay, and this equation is how the CWND is increased in slow start. Okay, every ACK will increase CWND by 1. And this equation tells us how CWND is increased in congestion avoidance. And here we can see that whenever there's an ACK, we do not increase CWND by 1 MSS, but by a fraction of an MSS. This is a fraction value. Okay. So there are many other things, subtleties, subtle details that we're not going to go into about the fast recovery. But I just went through with you the key points, the most important points. Okay, now let's talk a bit about the TCP throughput. So remember, definition of a throughput is how much data you send over an amount of time, right? It is expressed as bits per second, if you wish, or something equivalent. So it turns out that we can have a kind of do a kind of back of the envelope calculation for TCP throughput if as a function of the window size and the round trip time. And this is really back of the envelope calculation, and I will tell you why. So here we're going to make some simplifying assumptions that there is a window size at which there will be a packet loss. And we call it W loss, okay, W loss. Now, in reality, there's this window size at which there's packet loss. It's going to fluctuate over time, right? It keeps changing over time. It is not constant. But here, as a simplifying assumption, we assume that it is constant. Okay, if it is constant, okay, we're going to also make another simplifying assumption, is that when a loss happens, then the window will be divided by 2. Okay, so just to keep it simple, we ignore the plus 3, and we assume that it is not timeout. So with these assumptions, the window CWND will have this behavior if we plot it over time. right? So we start from this value, we increase it until there's a loss, because this is the value window size where there's a loss. When there's a loss, we reduce it back to half the value. We increase it again, we have a loss again, and so on and so forth, right? This kind of behavior. So if the window CWND is like this, then the average value of the window will be this value. This is the average value, right? Average between W loss and W loss divided by 2. It is 3/4 of W loss. 3/4 of W loss. So we can calculate the average TCP throughput. This is a very rough calculation. We can calculate it as the average window size divided by the round trip time. Okay, average window size divided by the round trip time. Essentially, because every round trip time you send the amount of data which is equal to the window. Okay, you send the window worth of data, and then the sender has to wait round trip time to get the act before it sends another window's worth of data. So this is a way to calculate the throughput if you do not have better information. But the exact definition of the throughput is that you need to look over an amount of time, right? So let's say X seconds, how many bytes have been transferred. Let's call it Y, right? You have transferred Y bytes. So the exact definition, the accurate definition of the throughput is that it is Y divided by X. Okay, so if you have the information to calculate Y and X, you should use Y divided by X. If you don't have more precise information, if the only information you have is average window size and round trip time, then you can use this formula. But this will be an approximation. And this is not the first choice to calculate the throughput. Okay, now let's look a little bit at the kind of new issues and challenges with TCP. So TCP, there's a kind of issue when you run it over what is called a long fat pipe. Long fat pipe. A long pipe, long simply means that you have a large value of round trip time. Okay, so you think it like a pipe, and you send something into the pipe. How much time does it take for that thing to exit the pipe? If you have a long pipe, it would take a longer time, right? So long pipe simply refers to a case where you have a large round trip time. Okay, fat pipe simply means that you have a pipe with a large diameter, meaning that you can send data at a high rate, right? A high rate. Okay, so the long fat pipe is the case where you have a high bandwidth, high rate pipe, but also large round trip time. Here we have an example, 100 millisecond round trip time, which is rather large. And let's assume that we want 10 gigabits per second throughput. Okay, 10 gigabits per second throughput. So this is fat pipe. This is long pipe. And further, let's assume that each segment is 1500 bytes, which is a very common value for the packets over the internet. Okay, now the question is, if we want to achieve 10 gigabits per second throughput over this pipe, if we want to achieve 10 gigabits per second throughput when we have 100 millisecond round trip time, how many segments do we need to have in flight? In other words, how big our window must be. How many segments must we have in the window? Okay, because we know that if we have a larger window, okay, that can help to maintain a higher throughput. Okay, so to answer this question, I am going to, so here I need to switch to, let me see. I'm going to switch to Word. And we're going to do some calculation. So here, let's look at the slide again. What we have is the round trip time, right? This is the round trip time. This is a throughput. So remember this equation. We have three items, right, in the equation. We have the window, we have the throughput, we have the round trip time. Throughput, window, round trip time, which means if you know two of them, you can calculate the third one, right? So it doesn't matter, right? So if you know, for example, window and round trip time, you can calculate the throughput. If you know the throughput and the round trip time, you can calculate the window, and so on, right? Because we use this equation. So that's what we're going to do here. Here we are given the round trip time. We'll be given the throughput. So we're going to calculate the window. I'm going to make this bigger. You just use the formula that we saw on the that slide, right? The back of the envelope calculation. Throughput is equal to window divided by round trip time. So here we are given the throughput. We are given the round trip time. We can use this equation to calculate the window. So I can just rewrite this equation to be throughput multiplied by round trip time. Okay. So here I just plug in the value, throughput 10 gigabits per second. That is what the slide says. Multiply by round trip time, 100 milliseconds. Okay, so now I just need to translate all of this into the same units to be consistent. So 10 gigabits is 10 gigabits per second. So 10 gigabits is what? To the power of 9, right? 10 to the power of 9 bits per second. Is that correct? Megabits is 6, 10 to the power of 6. Gigabits is 10 to the power of 9. Yes, thank you. And then 100 millisecond. So it's going to be 100. Okay, millisecond is 10 to the power of minus 3. Second. Okay, so it is going to be, this is 9. This is, okay, I can rewrite this to be to the power of 2. So this is going to be minus 1, so 10 to the power 8. Okay, 10 to the power of 8. Now, bits, right? Because I have bits per second and then multiply by second, bits divided by second, and multiplied by second. Okay, so it is equal to 10 to the power of 8 bits. But now, remember, we need to translate that into packets. So this is when I'm going to use this information. Each packet is 1500 bytes, right? Okay, so if I express it in packets, it's going to be, I have to divide by the size of the packet, which is 1500 times 8, 1500 bytes, right? Okay, now here I reached the limit of my mental calculation. I need to use a calculator. So if we use a calculator, we are going to have 10 to the power of 8 divided by 1500 times 8. And what we get is, okay, I think I may have, no, hold on. This is 10 to the power of 9, 10 to the power of 2 millisecond minus 3, minus 8, so 10 to the power of 8. Is that correct? Did I make a mistake? Okay, 10 gigabits per second throughput, 100 millisecond round trip time. Oh, sorry. Yes, oh, sorry, I understand your chat now. I had trouble to decipher it. So there is 10 gigabits, not 1 gigabits. So this is 10 to the power of 9. Thank you. Sorry. Okay, so 10 to the power of 9. So if I use my calculator, what I get is 83. Okay, so essentially, if I want to achieve a throughput of 10 gigabits per second, when the round trip time is 100 milliseconds, I need a window of this many packets. So if my CWND is less than this value, I will not be able to achieve 10 gigabits per second. So this shows us, essentially what this shows us is that when you have a large round trip time, you need a large window if you want to maintain the throughput, right? So these cases, this is called a bandwidth delay product. You multiply, so that's why we call product. And throughput correspond to the bandwidth, RTT correspond to the delay. Okay, so sometimes the long fat pipes, they are also referred to as large bandwidth delay product. Bandwidth delay product, right? Okay, so whenever, essentially what this tells us, if you want to achieve a high throughput, even with a kind of moderate value of round trip time, you need a large window. If you want to achieve a moderate throughput, but if your round trip time is large, you need a large window. If you want to achieve a high throughput, when the RTT is large, you need a very large window. Any question here on the concept of the bandwidth delay product? Okay, let's go back to the slide. Okay, so that's how we have this value, 83,333, which is what we calculated, right? Which is what we found from the calculation. So what do you think? What do you think about this value of the window? Do you think it's moderate? Do you think it's large? Yes, it's large. It's very large. It's very large. So what this shows us is that when you are in the case of long fat pipes or large bandwidth delay product, it is a challenge to maintain a good throughput. You need a very large window. Okay. Now, up to now, we have done the calculation without assuming no packet loss, nothing, right? We didn't assume any packet loss. Now, when you have packet loss, things get worse because, remember, when there is a packet loss, the TCP sender will reduce its CWND. Okay, the CWND will decrease. So that will affect your throughput. And you feel the effect even more when you have long fat pipes, because long fat pipe is when you need a large window. And if you have packet loss, then you cannot maintain a large window. If you have packet, and then your throughput is going to collapse. So this is this equation is simply just the point of this equation, so that you're not required to memorize this, but the point of this equation is that you need a very low probability of packet loss in order to maintain the throughput, some throughput, because I mean, if you plug in some values here, you can see. So here we have an example. If you want to achieve 10 gigabits per second throughput, we will need a packet loss rate of 2 times 10 to the power minus 10, which is extremely small loss rate. So these are the challenges when you run TCP over long fat pipes. And one thing, so actually what makes it worse is that, remember the effective window. Can somebody tell me what is the effective window for TCP sender? What is the effective window? Okay, what does the TCP sender has to do? There are two things. It has to do congestion control and what control? It had to do two types of control. Yes, congestion control and flow control. Okay, so to do the congestion control, it's going to maintain that CWND, right? So do that reset back to 1, slow start, congestion avoidance, and so on. So that is for CWND. Okay, now for the flow control, what does sender have to do? How does the sender do flow control? Restrict sending, but how? Okay, there's another variable, which is what? RWND. Remember RWND? Okay, let's do that here. I'm going to make this smaller. Okay, so CWND is the contraction window. And it is used for contraction control. But there's another variable maintained at the sender, which is RWND. And it stands for receiver window. And it's used for flow control. Okay, contraction window is the purpose of contraction window is not to overwhelm the routers on the path. The purpose of flow control is not to overwhelm the receiver. Now, because the sender has to do both, it has to do both contraction window and receiver window. So the actual window or effective window, if you wish, effective window is going to be the minimum of CWND and RWND. Any question? So this is the, at any given time, the sender cannot send more than the effective window before it has to stop and wait for ACK. Any question here? So this is the window that really determines the sending rate of the sender. Okay, because it has to do both congestion control and flow control. Actually, I'm going to change this a little bit. Oh, sorry, let me change this. This is better. Okay, so congestion control. To do congestion control, the window must be less or equal to CWND. Okay, to do flow control, now because it has to do both, any question on the effective window? Okay, so keeping this in mind, I'm going to go back a few slides. you remember this slide, the TCP header, and there is this field called the receiver window in the TCP header, and the TCP receiver will populate this field with how many bytes it has, it is willing to accept, how many bytes it has available in its buffer, and send it to the sender, right? So now if you look at this field, it is 16 bits. It is 16 bits. So with 16 bits, normally you can encode what is the largest value you can encode with 16 bits. It's going to be 64K, right? About 64K, which means normally because there's only 16 bits for the receiver window, the largest possible value of RWND is going to be 64K. 64K bytes is not a lot, right? So in our example, we needed 83,000 packets to maintain 10 gigabits per second. So this RWND may be a constraining factor, and in order to overcome that, they have defined what is called a window scaling option. So this is the name of a TCP option where the value that is put here by the receiver is not the actual value of the window, but to get the actual value of the window, it has to be multiplied by a scaling factor. Okay, so for example, if the scaling factor is 4 and the value here is let's say 64K, then the actual value of RWND is 64K multiplied by 4. Okay, so this is a way to kind of overcome the limitation of the 16 bits. And that can help in the case where we have long fat pipes because remember, we need a large window, and the window is the min of these two guys. So if this guy is constrained to be 64K, then the window cannot be greater than 64K. But with a window scaling option, you can have values greater than 64K. Any question here? Okay, are you still there? Just give me some signs and know that you are still. Okay, thank you. All right. Actually, I went a little bit over time, but let's just take a 5-minute break, okay, and be back at 1:55.